Hello and welcome everyone. Today we are solving the question rotate list. So let's get started. Given the head of a linked list, rotate the list to the right by k places. All right. So we're given a linked list in this question and we want to rotate it by k places to the right. So if we look at the given linked list, I assume it's like this. Yep. So let me try to annotate it. Yeah, we're given this linked list, which was the head of one, and they give us the head. Rotate the list to the right by k places. So what they mean by rotating it to the right by k places is basically they are, I think, the resulting rotate one. Yeah, that makes sense now. So rotate one. So what is k? K is 2 in this case. So I thought it was 5. So the k is 2, and after first rotation, 4 becomes the 5 becomes the new head, and 4 becomes a new head. And so we are sort of, the way I see this question is that we are taking this singly linked list, and we are if we refer to this node as a tail, we are attaching this node to the beginning. So in a default, like when we are just given as a, this is pointing to none, while from my intuition, I see that this is getting linked to this, and then our node is actually been rotated. So say our head is now from say from 1 changed to 5. That's how it looks, and then we are changing it to 4 again. So I see, so let's write it down. So in our understanding phase, what we see is that we are given linked list, rotated. Yeah, I think, but instead of writing it down like this, what I thought would be much useful is putting down sort of test edge cases or some cases that we might want to consider later. So what if say the linked list is empty, right? What we are going to do in that case? And then I think they give us the constraints here, and I also wanted to ask if k can be negative, but they say no, k cannot be negative. And the node values may range from 100 to negative 100 to positive 100, while the number of nodes in the linked list may range from 0 to 500. Right? So we might have just an empty linked list, and we might be, so given that, say, if there's an empty linked list, we can just return that empty linked list, right? Okay, so what if we only have, say, two nodes as an edge case, 2 nodes. So I think we might want to be rotating it within within those 2 nodes, right? So we are given this node of 1, 2, 3, 4, 5, and we have 0, 1, 2, and we're rotating it by 4. So when we rotate it 0, 1, 2 by 4, 2 becomes the new head, and then 1 becomes the new head, and then 0 becomes. So what we see from here is that multiple rotations are possible, right? So multiple rotations are possible, and k might be like a very big number. So I think we need to take note of that. And so yeah, so k bigger. Yeah, I wanted to use the code path Uh, I wanted to use the code pass umpire method, so I think uh, if I can just look at it's a completely different problem. I just want to see, okay, understanding phase. Or what are we gonna do in understanding phase? Establish the set of 2 to 3 test cases to verify their own solution later. Establish a set of 1 to edge case to verify their solution handles complexities. Have fully understood the problem and have no clarifying questions. Have you verified that any time space constraints for this problem? So I think we're good on this part, because since we said what if there are 2 nodes, what if the k can be negative? So I don't have questions. Regarding the test cases, I assume that say we have multiple rotations are possible, and I think the value of nodes don't really matter here. I guess they don't really matter. And then say, yeah, I think for now I'm good. So, and let's move to the matching phase, right? What are we gonna do in the matching phase? Stack what is the problem looks like to known categories of problems, linked list or dynamic programming. So it's definitely linked list, since we can see it actually right here. So, and the good part about linked lists is that there are not so many things you can do with linked lists. We often end up using pointers or some sort of manipulation that by changing the pointers, and then I think we can get the desired output. So yeah, I'm gonna clear my screen. Okay, I think I can do it. Not sure. Yeah, I got it right here, so I can just clear all drawings. Okay. Yeah. Let's go to the matching phase. So we said it's a linked list, obviously, and so my intuition, like if I were asked to solve this question, and I am solving this question, uh, I see that there is some sort of we are trying to link the end of the linked list to the head, and then changing the head pointer by k. So yeah, it might look like a easy way to approach this question, but I'm gonna try this and then see how it will work out. So say our head pointer is right here. So in my first iteration, what I want to do, I want to get the lengths of the nodes, right? So how many, or number of nodes, my apologies. So there are 3 nodes, and then when we reach the end of a linked list, right, I want to point it to the head back again. So I'm making it like a cycle, right? Basically, I'm making it a cycle. So we have this 3, okay? And why do we need the count of the number of nodes? Because we have the k, and we want, like, we don't want to do like those, like, say, multiple rotations. Actually, we want to divide it by 3 and then do remainder of times, uh, and then like do our manipulation sort of remainder of times, so that we don't end up actually traversing it like k times through the given no linked list nodes. So when we have, say, 4, right, we're back to this again. So we were on this, right, and then you can see that these two look exactly the same, right? So when you do the, say, I think it's rotation 1, right? It's rotation 1. So if you divide like 4 by 3, right? If you do like, say, 4 modular 3, it's gonna give you a remainder of 1. So doing rotating 4 times is exactly the same as rotating it only once. Say rotating 6 times is exactly the same as rotating twice. So we can get the combination from this particular method, I assume. So once we get there, we can say, okay, we have, say, whatever the k might be, we can just say modular it by 3 and get the remainder, and then change our head pointer, say, a remainder of times, right? So in our first things first, let's clear it again. So after the matching phase, we said, let's plan it, right? So according to my plan, what I want to do is get the count of nodes and make a cycle, okay, right? So we looked at how we can do the cycle. And then what I want to do is I want to change my head pointer a remainder of times. So say my yeah, oh wait. So if we only rotate it once, yeah, so if we are looking at this problem, we got a remainder of 1 and it's same as rotating it only once. So what we will do is that we take this 2, point it here, right? And then what we did was say we had a head pointer right here, right? So I think the problem with it's not a problem actually. What makes it hard is that so we make the 2's next pointer pointing it to the 0, right? And what we want to do, say we want to make the 2 a new head, right? So it should be 2, 0, 1. So we have, so there are two things that are actually happening here. We are taking this node, right? And then we are sort of getting rid of the uh, pointer to it. So we're getting rid of the pointer from it. And then we are setting this pointer, this node itself as the head. So let's write it down. And then we are making the, yeah, since we already linked it to 0, we don't have to do anything. So it's gonna be head 2, 0, 1. Say if we are rotating only say twice, right? How we're gonna go about it. So we have this link, and then we say, okay, it's case 2, like say the remainder is 2, and we want to change the head twice. So we take, so we do this approach, right? But we are not removing the, say, we're not doing it as exactly as this in our rotation 2. What we are doing is that we are linking 2 to 0, yes, but we are changing 0 from 1. Yeah, we're changing the head to 1 and then removing the previous from it. So I think it can get pretty complicated if we don't have this things clearly laid out. So I think we need to come up with a specific method where we can just say, okay, I want to manipulate it this way or this way. Okay, if the remainder is 1, say it's gonna be this node, right? This node is gonna be the head. If the remainder is 2, it's gonna be this node. Or 4 is gonna be, so it's always gonna be in range of 3. So if it's gonna be the third node, it's gonna be exactly the same. So it's 3 modulo 3 is 0. So it's always gonna be in the, say, range of nodes counts in our linked list. And then say if it's 2, right, we want to make the second one from the end, the head node, right? So I think we can just traverse all the way up here. yeah, we can just come all the way here and then have a previous pointer to it, right? We want to have a previous pointer to it. So we can just say this one should not have a pointer here. Instead, what we want to say, oh, but interestingly, this one is not linked, right? So I think we also need to take care of that. So I'm thinking of doing it in the end. Yeah, I think I can just do it this way. Yep, exactly. Yeah, so I can just do it this way. And then remove the pointer from here. Say if the previous, I'm just gonna say p dot next. So if the previous dot next is equal to 1, remove the pointer, make previous dot next as the head, and link the linked list. Right? So I think I kind of have the ideas here. So first things first, we want to count the number of nodes. And I want to get the remainder. What if the, yeah, that's also, what if k is less than, what if k is less than number of nodes? We should also take care of that. And then say, we get the count of number of nodes, right? And then we say traverse, as you say, previous dot, while previous dot next is not equal to, so we want to say, I think if I'm targeting this node, right? So it was 2, remainder of 2. I had the remainder of 2. No, I think it's, yeah. So in this case, just 1. So remainder is 1. So I'm targeting this. So I can just say, yeah. So I want to come all the way up here and then kind of remove the pointer here and then make this one a head and then link it back to 0 again. Yeah, so count number of nodes while previous dot next is not equal to, so we have this remainder thing, right? So get the remainder of nodes, get the remainder, and it's gonna be that one from, so I think I can say number of nodes minus the remainder, right? So it's gonna, if this is 1, so I can just say we had 3, and then I can just say 3 minus 1 is 2. Yeah, I can just go all the way. Yeah, that makes sense. Sorry, it makes sense to me, but it might not make sense to you. But as we will code it, I think it will make more sense. So I can just say count is gonna be equal to 0 at first, right? While at, so I think I can just say temp is equal to head. While temp, I want to traverse. Here I'm getting the count nodes, right? While temp count plus equals 1. And temp should be equal to temp dot next. So here we are just counting the number of nodes. And then we have k, so remainder, I'd say remainder is going to be equal to k modular 3. Oh, not the 3, but count that. So we get the count remainder from here. And then I can say, so we have the count number of nodes. And then say we had 3 nodes. We had k, which is 4, and then 4 modular 3 is gonna be equal to 1. And then we want to say k minus remainder. So this is going to give us the last target node, right? Target, so this is the number of like nodes we want to traverse in order to get that particular node that we want to make to be ahead. So target, we had 3, 4 minus 1 is going to be 3. Oh, wait. K is 4, count is 3, and we got the remainder of, and then we want to, we want to get it from count minus remainder. All right, count minus remainder. We got the target. So our target is this one. So we will traverse all the way. So since 3 minus 1 is 2, we only want to traverse 1 and 2. Okay, we say while target. So I think we'll also need another temp, gonna be equal to head. I can just say previous, right? So I want to say previous dot next. Previous is equal to previous dot next. So I had my previous pointing right here. It was target of 2, and then I want to subtract my target, minus equals 1. So it becomes 1. And then here I come, and then my target becomes 1, and I can just traverse it again. Wait, do I want that? The 2, 1. Yeah, target was actually 2. So I can say previous dot next is equal to head. So I think I need to, yep. So my previous is pointing right here. So, and it's 2. And then it comes here, it becomes 1. Then it comes here, it becomes 0. Yeah, so we have the previous. And what else? We have the previous going, so after that, we want to point, say 1. Wait. Yeah, we want to just remove the pointer. Say remove the pointer, right? Before I remove the pointer, say I can just save it as a temp, which will be so temp is gonna be equal to previous.next. So we are targeting this 2 as temp. So this is temp, this is our previous, right? And then we wanna say temp.next should be pointing to the current head, and then we want to make point temp. Oh wait, but what if, yeah, what if it's just 1? We're removing 1. That's interesting because we don't want to point the 1, right? We don't want to say point 1 to the head. No, I don't want that. I cannot just do that. So I want to traverse all the way till the end, right? Go all the way to the tail and connect to yeah, while temp dot, so I can say, so new head is gonna be equal to temp, right? So I just save this. Before that, I can just remove the pointer. So previous dot next should be pointing to none. And new head is just temp, right? And then I want to say while temp dot next, temp is gonna be equal to temp dot next. And when we reach the temp dot next null, we can just say temp dot next should be pointing to the head, and then we can just return the new head. Yep, I think this is what I would do. So let's see, we're counting the number of nodes, temp head, and then we are saying we are getting the remainder, which is in this case will be 4 modulo 3, which is 1, and count minus remainder, which is going to give us 2. And then we say previous dot next is equal to head. We say while target previous is equal to previous dot next. So from here we come all the way here, and then we said save this as a temporary value, right? We save this as a temporary, and then we say while temp dot next. So there's nothing after temp, right? So we can just point this to the current head and return the new head. I think this works. So this works, but what about the others? Say when the K is so I think say if it's 1, right? And 1 modular 3 should, I'm not sure. I think I need to look it up, because if K is less than, say, the number, the count itself. So 1 modular 3 would give us 1. 2 modular 3 would give us 2. Exactly. So I think we don't have problem from that way. So I think I need to initialize it. Temp, well, yeah, this node 0. So 2 cases pass that we have so far. Not sure if the other's gonna pass. Uh-oh. Yeah, so if there is no head, right? If there is no head, we just want to return. What if there is, say, just 2? What's gonna happen if there's only 2? So say we have the 2 and we have 4. I think it should work. Oh, okay. Say we have the 1. If not head or not head dot next. I try again. So 7. So K is 0 here. I'm not sure why. Say, I think there should be a way. Say what happens if it's just 1, right? Say if it's just 1, K is just 1. Yeah, I think we will have no problem if it's just 1. But if it's 0, we are having a problem. K is equal to 0. Try again. These weird edge cases. We have 1 and 2 and the 2. Okay, so we have 1, then we have 2, right? Since we have 2, the 2 modular 2 should give us 0, right? So the result should be I'm gonna use this as a test case, say 1 and 2 and 2. So we have where we are getting this error. Right? Let's see. Okay, here it says non-type value. How come temp is none, right? Is it because, say, temporary is gonna be previous dot next? What if I just do this? Well, temp and temp dot next. What? So I don't really understand what is happening here. So say previous. I want to print out the value of I think it's just 2. We have the count, which is say temp dot next remainder is so k is gonna be here 2 and the count is also 2. So I think 2 modular 2. Oh, this is gonna give us 0. I can just say that's what I was assuming. So if remainder is equal to 0, just return the head. This means there were no changes. Changes needed. Yes. I wasn't actually expecting that this is gonna pass. But yeah, thank you guys for watching. And the time complexity is big of n for this problem because we're only gonna be traversing through this only once. I'm so happy. So glad that it worked out. Sorry it took you a little bit, but here we are.